Hi everyone. In this lecture we are going to get into seismic waves, the different types of seismic waves and how they travel, as well as the different hazards that are associated with earthquake activity. So the goals of this section of the lecture are be able to explain how seismic waves can locate epicenters, explain earthquake strength, and discover more about the center of the Earth, as well as explain primary and secondary earthquake damage mechanisms and the different factors that affect it, as well as distinguish between tsunami and regular storms, explain how tsunamis actually cause so much damage and what types of faults they occur on, as well as discussing the many different ways that earthquakes can cause damage and injury, and a little bit of earthquake preparedness. So seismic waves originate at the earthquake focus, and there are two types of seismic waves. There are body waves and surface waves. Body waves travel through the Earth's interior. They travel through the body of the Earth. Surface waves can only travel along the surface of the Earth, so the outer part of the Earth. Within each of those, there are a couple of types of waves. So for our body waves, those that travel through the center of the Earth, we have P waves and S waves, the primary waves and the secondary waves. Primary waves travel the fastest. Secondary waves are next, the second fastest. Surface waves travel slower. It takes longer for surface waves, for example, to start at this focus here and get to this seismograph station that is measuring the waves, because they are traveling only along the surface of the Earth. They can't actually travel through the Earth. Surface waves are the slowest type of waves. So the body waves and the surface waves are both recorded by what we call a seismograph, and is recorded into what we call a seismogram. So a seismogram is a piece of paper, generally that will show these lines for any type of motion. Seismograph is the machine that is actually recording any motion that it picks up. So the seismographs will measure both body waves and surface waves. So the waves occur in a very distinct order. They always arrive in the same sequence because we know the set speed that these waves travel. So there will always be primary waves arriving first, and then the secondary waves, and then the surface waves. So any seismogram of an earthquake, you will always be able to see, not that it's easy to always pick out, but you can always see the primary wave arrival, then the secondary wave arrival, and then the surface waves. So they always arrive in this sequence: primary, secondary, and then surface. And that's because they travel at a set speed. So we know primary waves are the fastest. They're going to travel from the focus to any seismogram faster than the secondary waves and the surface waves. So when we think about these waves, what are the differences? So they move in different ways. So body waves are P waves and are S waves. They can move through the interior of the Earth. P waves, the fastest waves, they deform rock in sort of a expansion compression pattern. So here you're stretching and then squishing and stretching and squishing. So you're expanding and compressing as the P waves travel. S waves, they deform rock by displacing perpendicular to the direction of the wave travel. So if the wave is traveling this way, the S wave is going to make zigzags. And I have a video to show, I think on the next slide, that is a little bit more clear. So The P waves always arrive first, the S waves always arrive second, and they are a different type of wave, so they move and deform rock differently. So here first they show the P wave motion using this slinky. So there is compression and expansion as this P wave is moving. And then we have an S wave. So this is showing the S wave. The S wave deforms the rock perpendicular to the direction of the motion. So we have that zigzag perpendicular to the direction of the wave motion. So the P wave and the S wave deform rock in really different ways. So here we have another example of the primary wave, the P wave, compression waves. So we have stretching and compression and stretching and compression. These you generally will feel a sudden jolt. They move very, very fast, and they can sometimes be heard as a low rumbling. Primary waves are also unique because they can move through any medium. So solid, liquid, or gas, the waves can move through. Secondary waves, they move like a zigzag perpendicular to the direction of the wave motion. So this is what's going to make it very difficult to stand. So these waves, when you feel these waves hitting, and if it's strong, trying to walk across the apartment, you're going to fall over. It's going to be really hard to stand up and walk. They are not as fast as the primary waves, but they are more destructive. So the way that these waves move and deform through rock, these are the waves that cause a lot of the destruction. So these are body waves. They move through the center of the earth, but they cannot move through liquid or gas. So primary waves can move through liquid and gas. So for example, through the ocean. The primary waves can still move through the ocean. The secondary waves cannot. They can only move through solid earth. So our surface waves are those that move along the surface of the earth. So they don't travel through the interior at all, and they're much slower than the P and the S waves. These are generally the most destructive and what you feel the most of in an earthquake. So oftentimes the P waves, the primary waves, are not felt. The secondary waves can be felt, and then the surface waves are what really cause all of the destruction. So the main two types are the L wave and the R wave, the Love wave and the Rayleigh wave. Love wave is sort of a zigzag pattern. Rayleigh wave travels like ripples on the surface of water, or like waves in the ocean. So here we have our surface waves. They generally combine to create a really long rolling motion. So you have zigzag and up and down motion. This can be incredibly destructive. And it can be very similar to when there are big waves in the open ocean. So not crashing waves, but some large swell out in the open ocean. So surface waves are what's going to cause the most destruction on the surface of the earth, of buildings and roads and trees and things like that. They move much slower than the P and S waves. So if we are reading a seismogram, remember that the waves always arrive in sequence. We're always going to see the P wave, then the S wave, and then the surface waves. When we are using our seismogram to try and locate or time our earthquake, really what we want is the P wave and the S wave arrival times, because we can use the difference between the two, or the P to S wave interval, so the time between the arrival of the P wave and the arrival of the S wave, to tell us quite a bit about that earthquake. So here we have an example of a seismogram. So here we see a small blip, that is the arrival of the P wave. Here we have a bigger blip, that is the arrival of the S wave. And then here we have the seismogram really goes crazy. Those are the surface waves, causing a huge amount of shaking on the surface of the earth. So these are in time. So in this case, we have 1 minute intervals between each line. So we can calculate the time difference between the arrival of the P wave and the arrival of the S wave. That's going to be very important in your lab today. So when we are measuring earthquake strength, we can use a couple different ways. So we can measure intensity, which is shaking and damage. So this is really qualitative and occurs after the earthquake happens. So after the earthquake, you can go out and see the type of damage that it caused. That is going to be measuring the intensity of the shaking, the intensity of the quake. Whereas magnitude is using the measurement, so using the seismogram to get a quantitative measurement of how strong was that earthquake. So I'm going to go through a couple different ways that earthquakes can be measured. This is the intensity scale. So generally the intensity is between 1 and sometimes 12 in Roman numerals. So intensity 9 or 10 is the most damage, 9 or 10 up to 12, the most damage, but this scale is really based on after the earthquake going outside and mapping, okay, where are all of the buildings collapsed? Where are all of the trees knocked down? Where do we have cracks in the ground and pipes breaking? Versus a little further out from the earthquake where maybe we just have a few walls crumbling or windows breaking, but we don't have as severe damage. So the earthquake intensity is going to decrease with distance from the epicenter, from the center of the earthquake. So the Richter magnitude scale is based on the maximum amplitude of the seismogram. So this is a more quantitative measurement. We're actually looking at the magnitude of the shaking of the measurements. Deep earthquakes, we should note, don't generate surface waves as well as shallow earthquakes. So deep earthquakes are not going to have as severe surface waves as an earthquake that starts at the surface. So that isn't measured, as well as the time of shaking or the amount of time of shaking is not considered in this scale. So we're just only looking at the maximum amplitude, and that's it. So the time at that maximum amplitude, the time it took to get to that maximum amplitude is not considered when we're looking at the Richter magnitude scale. The moment magnitude scale, however, looks at the total energy expended during the earthquake. So it takes into account the strength of the rock, the fault area, and the slip distance on the fault. So how much or how far did the fault actually slip? So this scale takes into account the strength of the shaking and the amount of fault movement. So this kind of looks at both. The moment magnitude is going to look at the whole earthquake, not just a piece of it. And in a moment magnitude, with the moment magnitude scale, we can translate that into how much energy was released. So for example, here's a graph. We have the magnitude, the moment magnitude scale. We have energy released in terms of kilograms of explosive. And then we have the number of earthquakes per year. So for example, a magnitude 1 or 2 has a very large amount of earthquakes, whereas a magnitude 9 has very, very few earthquakes per year. And then they've also plotted energy equivalents. So I like this graph because it gives you some things to compare to. So a moderate lightning bolt gives off the same amount of energy as about a 2 or a 3. A large lightning bolt is about a 3 or a 4. That would be a minor earthquake, which is felt by most people. An average tornado would be more like a 5, where we would start to see some property damage. The eruption of Mount St. Helens, for example, would be up there at a magnitude 8. So here we're going to have a major earthquake, large loss of life, severe economic impact, and a huge amount of energy released. So the magnitude takes into account what occurs on the surface as well as the actual energy that is released in that earthquake. So the tricky thing about the moment magnitude scale is each whole number from 1 to 10 each increase of one whole number corresponds to an increase in 32 times the energy. So to get from an M6 to an M7, you would have to have 32 M6s to get to an M7. So it's not a one-to-one scale. Moving up one from M1 to M2 or M4 to M5 is an increase in 32 times the amount of energy. So let's think about our seismographs and actually using them to locate the epicenter of an earthquake, because we don't have seismographs everywhere on Earth on every single street corner or every single spot in the ocean. We have to use the data that we have. So we have to use the seismographs that we do have to be able to determine where did that earthquake occur. We feel some shaking, okay, great, but it wasn't that strong here. Where did it start? Where is the epicenter? So we know that the P and the S waves travel at different speeds, but we know that their speeds are very set. So we can use the difference between a P and an S wave arrival time to determine how far away the earthquake is from that seismograph. So here we have the P wave plotted and the S wave plotted in terms of distance versus time. So those are constant. Those red lines are constant. Then all we do is we take our stations 1, 2, and 3. Let's say we have 3 seismograph stations with 3 different seismograms, and we will measure the difference in arrival time from the P wave to the S wave. Then we can plot where that difference falls on this graph. So the difference between the P wave and the S wave, between the P wave and the S wave, and it's going to correspond with the distance that the earthquake's focus is from that. So for example, we can use this epicenter distance versus travel time to determine the distance from our seismogram to the focus of the earthquake. So let's say our seismogram logs a difference of 3 minutes. So the P to S wave interval is 3 minutes. So it took 3 minutes between the P wave arrival and the S wave arrival. So we want to see how far is our seismogram from the epicenter. So we're going to want to find where there's a difference between the P wave arrival and the S wave arrival of 3 minutes. So if we look at this graph, we want to find where the difference is only 3 minutes. So we would find that right at 2,000 kilometers, we see the difference between the P wave arrival and the S wave arrival is 3 minutes. So there is a 3-minute difference. That means that our seismograph is located 2,000 kilometers from the focus of that earthquake. So from there, we can do that with 3 different stations. Let's say we find station 1, 2, and 3. We have 100 kilometers, 200 kilometers, and 400 kilometers from our different stations. We use what we call triangulation. So we can draw a circle from our seismogram. Say we're in Southern California. That shows a circle of radius with 400 kilometers. We have our other stations here, and where they overlap, when you have 3 stations, they will triangulate, hopefully perfectly, to an exact spot. That is where our earthquake originated. So if we have just one station, we know that the earthquake would have happened anywhere along this circle, but we don't know the direction that the earthquake came from. So we don't know, other than it's around this circle, it's 400 kilometers away, whatever the distance is, we don't actually know which direction it came from. So in order to determine the exact location, we need to have 3 different seismograms to triangulate and to conclude on one exact spot as the earthquake epicenter. So that is what we do in real life. So we draw circles around each station with the radius equal to the distance from the epicenter. And we have our 3 circles. They will overlap and combine on one point that is the epicenter of that earthquake. So some of our largest earthquakes have happened along what we call our ring of fire. If you remember from our plate tectonic lessons, there's quite a bit of plate tectonic activity. Our largest earthquakes, we have had a couple in the magnitude 9 or above. In Chile, Alaska, Sumatra, over here, as well as Japan, we've had 9 or above magnitude earthquakes. So if we look at the San Andreas Fault, you might have heard that the San Andreas is due for a rupture. That is because on average, large earthquakes occur on the San Andreas about every 150 years, and we are a bit overdue down in Southern California. So overdue just in the fact that statistically there have been more frequent eruptions than what we have had recently. So earthquake destruction, the destruction that we see, really depends on the magnitude of the earthquake, the distance from the focus, and both the intensity and the duration of the vibrations, and then what material we're actually dealing with. So there's quite a different, there's a few different types of destruction that we often see with earthquakes that I'm going to go through quickly here. So our ground, shaking, displacement, so depending on the different types of waves, we're going to have different motion, and they always happen in the same sequence. Remember, we have our P waves, our S waves, and then our surface waves come next. So the surface waves are what's going to cause the most destruction. So something common that occurs during heavy shaking is called liquefaction. So this is where our soils will actually behave like a liquid. So before our earthquake, we see on the left there the oranges. These are representing grains of sand or soil. So they are in a rather unstable situation. They're being packed, but that is how they are situated. There is maybe some water in between the grains of soil, or let's say our oranges. They're in a box, they're in their location, they're stuck there. However, if you set them free and then set some shaking, they are going to situate themselves in a more stable packing, which would be in this hexagon shape. So what that means is there is less water in between the grains of soil. So instead of having this much water, we now have a lot less water. The extra water is going to move to the surface. So what this does is it causes soil to harden into an almost cement. And then there will be a layer of excess water sitting on top. So this can be incredibly hard to deal with, incredibly hard to get things out of liquefied soil. So I have a video to show you a little example of how this happens. So here he has some moist sand. It's not totally saturated, but it's not completely dry, so there is some water in there. There's a weight and a golf ball. So the weight is to show a building, let's say. The golf ball is to show anything that would be underground. So he will imitate the shaking of an earthquake. So you notice that as the heavy object comes up, the light object goes down. There's a layer of water on the top. It would have created a sort of cement. The sand was a lot harder afterwards than it was before. So here's an example. This building was totally toppled and swallowed up in the 1980s in Mexico City. So this can cause a huge amount of damage that is also incredibly difficult and expensive to rectify. So earthquakes also cause landslides. So often shaking can cause slopes to fail. So definitely in Southern California in the 1994 earthquake, there was a huge amount of property damage due to just landslides alone caused by that earthquake. And then there are also fires. So displacement can break pipes and break power lines and gas lines, which can cause the ignition of fires. This can then be extra hard to put out because the water lines are also broken and the roads are trapped, so the firefighters can't get to the station, get from the station to the fire. So fires during the time of an earthquake can be incredibly dangerous. In the big earthquake in San Francisco that destroyed a lot of the city, actually 90% of the destruction was due to fires caused by the earthquake. So that was actually a really big part of the destruction, was that so much was able to burn during or immediately after that earthquake. And then tsunamis. So tsunamis are a result of displacement of water. This happens due to large offshore earthquakes. So tsunamis only occur when there is vertical displacement of water. Only vertical displacement of water. There has to be vertical motion in order to displace water vertically. There has to be vertical motion in order for there to be a tsunami. So here we have our subducting plate. So we know there's vertical motion in subduction. As our subducting plate is subducting, the top of this, there's going to be a lot of friction of our overriding plate. It's going to get a little bit stuck. It's going to have some slow distortion. Eventually, it's going to slip back into place. There's going to be a big earthquake, and a huge amount of water is going to be thrown up into the air. The tsunami waves will then spread out like ripples from that focus. So here is a cartoon video to better show how tsunamis are formed. So here's our subduction. And then this friction is overcome. It shoots upward. It causes a huge vertical displacement of water that then moves outwards in circular ripples. Emphasis on plural ripples. So it's not just one wave from that earthquake center. So remember that earthquake-generated tsunamis must occur where there is vertical displacement. So it has to be a dip-slip fault. It's never a strike-slip fault. It's never a transform boundary. So here is a map of hazards for tsunamis, and you'll notice that Southern California, where we have our transform boundary, is quite low. So where there is no vertical motion, vertical displacement nearby, we do not see a very high hazard. Only where we have those dip-slip faults, especially the subduction zones, is where we're going to have the greatest hazard for tsunamis. So more recently, the Indian Ocean tsunami in 2004, the epicenter was near Sumatra, around here. The rupture extended really far north. It was a absolutely horrible and very, very, very devastating earthquake and tsunami. The tsunami hit parts of Indonesia in minutes. Within minutes, there was absolutely no warning time. And it caused pretty complete devastation. Entire communities were erased. Here is an example. So here was a satellite image from right before. Then after that tsunami wave and set of tsunami waves, this is what it looked like after. So almost everything was completely erased. So tsunamis can be absolutely incredibly devastating and very, very horrible. So here is a little summary of an article from someone who survived a tsunami. So his advice was to listen to warnings. So listen to warnings. If you see or hear warnings, listen to them because they are serious. Generally, when you have a big displacement of water offshore, the waves are going to retreat. So the water is going to retreat very significantly, very quickly, and way more than it normally would. That is a sign that the water is about to come back and it's about to be a tsunami. Also expect a lot of waves. So a lot of people don't realize that the tsunami waves travel in ripples from that center, but it's not just one wave. It's not just one big tsunami. It's many, and they can last for many hours. And the advice is to get to high ground and stay there. So be prepared for roads to be impossible to travel through. So get to the highest place you can, grab something that floats, and stay up there. If you ever find yourself in an area where you hear there is a tsunami warning or you see the signs of a tsunami coming. So in terms of predicting earthquakes, it's very, very, very difficult. So we can use statistics to say this place ruptures often, this place ruptures every, say, 300 years. But other than that, it's very, very difficult. So earthquakes do have precursors. So here, foreshocks, which are smaller shocks before the large shocks. Strain in the crust, level changes in wells or gases, new gases in our well water, and also unusual animal behavior. But these signs are very, very difficult to put together and can be very difficult to actually separate from just normal variations. So these are not used to predict earthquakes. They're often seen, in hindsight, that earthquake now explains why we saw the level changes in the wells. But not all of these things happen at the same time, so you wouldn't expect to see all of these, or you wouldn't expect to see or notice any of them before the earthquake actually occurred. We do have seismic hazard maps. So this is just looking at the history of earthquakes around the world, where has the highest hazard of having more earthquakes, and stronger earthquakes, where has the lowest hazard. So you'll notice in Southern California, we have a very high hazard because historically we have had many earthquakes and strong ones. So here again is the San Andreas Fault. So there's some sections of the San Andreas that are creeping. So we really wouldn't expect large earthquakes. Where we are, we would. These are regular slip-producing small earthquakes. But we have not had an eruption in almost 300 years, over 300 years. Whereas statistically, there would be an eruption every 150 years. So when people say we are overdue, that's just because statistically, on average, the San Andreas ruptures every 150 years. And now it's been about 300 years since the last eruption. So yes, eventually the San Andreas will rupture. There will be an earthquake or earthquakes. But the impacts are really going to vary hugely depending on how large is the earthquake, how large is that rupture, what type of shaking do we see, what time of day is it, what are the weather conditions, are there aftershocks, are there many aftershocks that are really small, are there a few that are really big? There's a lot of things that will factor into how a San Andreas fault rupture will actually affect us. So what to do when you feel an earthquake coming? If you're inside, stay inside. There is generally not enough time to move very much, and a lot of injury comes from trying to move when you're in an earthquake. The main thing that you should do is get under a big piece of furniture, something sturdy, a table, a desk. Cover your head and hold on to that object. So do not go to elevators. If you're outside, try and go to open ground. If you're inside, try and get somewhere where nothing will fall on top of you. So you want to be under a strong piece of furniture like a table or a desk. Since we live in earthquake prone area, I suggest everyone have an earthquake kit, an earthquake disaster kit. If you want more information on what is suggested to have in your earthquake kit, that link is right here. So I have one. We have a lot of water, canned foods, first aid kit, flashlight, dog food, the necessary things. They say you should prepare for 3 days of no water and no food access in your earthquake kit. So just to be prepared in case anything does happen and our water lines are broken, the gas lines are broken, the wall of your house falls in, something like that, you should be prepared with some food that you can take and go, especially water. Water is the most important part.